We have series RLC circuit. In order to find total impedance, I'm supposed to find first the inductive reactance and capacitive reactance, because I have the given inductance and I have given capacitance. Also, I have given omega. So we have to write the formula for X of L first. X of L is equal omega L, where omega is equal 1 times 10 to the 6th, of course, radians per second, times L, which is equal 500 microhenries. This is equal 500 ohms, and don't forget that inductive reactance has to be written with the angle of 90 degrees. If you prefer to use rectangular form, you're supposed to write J 500 ohms, but we are going to work with the polar form. Next, we're supposed to find X of C, capacitive reactance. The formula is 1 over omega C. This is equal 1 divided by omega 1 times 10 to the 6th radian per second times capacitance, which is equal 10 nanofarads, close parenthesis, and this is equal 100 ohms and angle of negative 90 degrees. Okay, so this is my capacitive reactance. In order to find Z total, don't forget that we have series circuit. We're supposed to write the following formula. Z total is equal resistance plus X of L plus X of C. Okay, when we have series circuit, we're supposed to add all impedances together, but don't forget that we're supposed to include angles, because if you are going to forget about angles or J's, if you use rectangular form, your answer is going to be wrong. So we have R equals 320 ohms plus X of L, which is equal 500 ohms, and angle of 90 degrees, plus X of C, which is equal 100 ohms, and angle of negative 90 degrees. This is equal 512.25 ohms and angle of 51.34 degrees. Okay, so please notice that we got positive angle, so it means that the impedance of the inductor is greater. So next we're supposed to find I total. In order to find I total, I'm going to use Ohm's law. I total is equal voltage source over Z total. Please notice that the voltage is given in the form of the sinusoidal equation, so that's why we are talking about peak voltage. So we have 12 volts over Z total, which is equal 512.25 ohms and angle of 51.34 degrees. This is equal 23.42 milliamps and angle of negative 51.34 degrees. So this is the total current in my circuit. Don't forget that in series circuit, the current is the same at every single point in that circuit. So I can write that I total is equal to IR, this is also equal to IL, and this is also equal to IC. Next, we're supposed to find voltage across the resistor. in order to find voltage across the resistor, I'm going to use Ohm's law. VR is equal IR times resistance, where IR, we said, is equal 23.42 milliamps and angle of negative 51.34 degrees times resistance, which is equal 320 ohms. This is equal 7.49 volts and angle of negative 51.34 degrees. So this is the voltage drop across the resistor. Next, we're supposed to find voltage across the inductor. Again, I'm going to use Ohm's law. VL is equal IL times X of L, where IL is equal to IR, 23.42 milliamps, and angle of negative 51.34 degrees, times X of L, and X of L is equal to 500 ohms, and angle of 90 degrees. This is equal 11.71 volts and angle of 38.66 degrees. Okay, so this is the voltage across the inductor. Next, we're supposed to find voltage across the capacitor. VC is equal IC times X of C. So again, I have 23.42 milliamps, an angle of negative 51.34 degrees, times X of C, and we found that X of C is equal 100 ohms and angle of negative 90 degrees. This is equal 2.34 volts and angle of negative 141.34 degrees. So this is the voltage drop across the capacitor. Now we're supposed to verify if our answers for voltages are correct. Please keep in mind that in series circuit, if you are going to add all voltage drops across each component, you're supposed to end up with the value of the voltage source. Means we have to use KVL, Kirchhoff voltage law. So if voltage source is equal voltage across the resistor plus voltage across the inductor plus voltage across the capacitor. So I have VR equals 7.49 volts and angle of negative 51.34 degrees plus 11.71 volts and angle of 38.66 degrees plus 2.34 volts and angle of negative 141.34 degrees. Your answer is supposed to be 11.99 volts and angle of 0.022 degrees. Now we're supposed to compare this value with given voltage source. The voltage source has value of what? 12 volts and angle of 0 degrees, and we obtain 11.99 and angle 0.022 degrees. So we can say this is 12 volts and angle of 0 degrees. So it means that our calculations up to this point are okay. Next, we're supposed to find the true power. Okay, so we're supposed to write the formula first. P true is equal, because I'm dealing with the peak values, I'm supposed to write 1/2 IR to the second power times the resistance. So I have 1/2 times the current, 23.42 milliamps, raised to the second power times the resistance, 320 ohms, is equal 87.75 milliwatts. So this is the true power in my series circuit. Next, we're supposed to find the reactive power. We have to find first the total reactance. Okay, so I'm going to write xt is equal x of L plus x of C, where x of L we found is equal 500 ohms and angle of 90 degrees, plus x of C, which is equal 100 ohms and angle of negative 90 degrees. This is equal 400 ohms and angle of 90 degrees. This is my total reactance in my circuit. Next, I'm supposed to just use formula for reactive power, which is going to be 1/2 I total raised to the second power times the total reactance. So I have 1/2, and the total current is 23.42 milliamps raised to the second power times total reactance, which is equal 400 ohms. Everything is equal 109.69 millivolt ampere reactive. Okay, so this is the reactive power in my circuit. Next, we're supposed to find the apparent power. S is equal 1/2 I total raised to the second power times Z total. This is equal 1/2 I total 23.42 milliamps raised to the second power times Z total, which is equal 512.25 ohms. And this is equal 140.48 millivolt amp. Okay, so this is the apparent power in my circuit. Next, we're supposed to find the parallel equivalent circuit. In order to do so, we're supposed to write the formula for total admittance. Total admittance is equal 1 over Z total. Now, I would like to ask you to switch your calculators to the rectangular mode. I want you to plug in the values into the calculator and get the answer in the rectangular form. So this is equal 1 over Z total we found is equal 512.25 ohms and angle of 51.34 degrees. This is equal, okay, we are talking about the rectangular form from this point, right? So we're going to get 1.22 millisiemens minus J 1.52 millisiemens. Okay, so this is my conductance and this is my inductive susceptance. Why inductive susceptance? Because we have negative sign next to J, okay? And we are talking about the admittance, okay? So this is the total admittance expressed in the rectangular form, where the real part represents the conductance and the imaginary part represents susceptance. But if we have negative sign, it means that we are talking about the inductive susceptance. So it means that in parallel equivalent circuit, we are going to have two components. We are going to have resistor and inductor. In order to find resistance, I'm supposed to simply write the formula. R is equal, I'm going to call this RP, means resistance from the parallel equivalent circuit, is equal 1 over G. So this is equal 1 over G, 1.22 millisiemens, is equal 819.67 ohms. So this is my resistance. And if I want to find the inductive reactance, X of LP, parallel, okay, P stands for parallel, is equal 1 over BL. So I'm going to have 1 divided by 1.52 millisiemens, okay, an angle of negative 90 degrees is equal 657.89 ohms, an angle of 90 degrees. Okay, so this is the inductive reactance in my parallel equivalent circuit. Next, in order to find the inductance in my parallel circuit, I'm supposed to use the formula for the inductive reactance. So if X LP is equal omega LP, where in order to find LP, I'm supposed to divide both sides equation by omega, and I'm going to obtain the formula LP is equal X of LP over omega, which is equal 657.89 ohms divided by omega, which is equal 1 times 10 to the 6th radians per second. This is equal 657.89 microhenries. Okay, so this is the inductance in my parallel equivalent circuit. Now we can draw the circuit. So I'm going to use this space over here. I have voltage source, and I got the resistance over here, and this is my resistor RP, which has value of 819.67 ohms, and also I have inductor. I'm going to call this also LP, which has value of 657.89 microhenries. So this is my parallel equivalent circuit. Next, we're supposed to find the true power and reactive power for the parallel circuit. True power in my parallel circuit is equal 1/2 voltage across the resistor in my parallel equivalent circuit raised to the second power over the resistance RP. Okay, so this is my parallel equivalent circuit. Please notice that the voltage across the resistor and voltage across the inductor are going to be equal to the voltage source, because this is parallel circuit. And in my formula I'm going to use also VRP, which is nothing else just voltage source. So I'm supposed to simply write this as 1/2, and my voltage across the resistor is equal to the voltage source, which is equal to 12 volts raised to the second power over RP, which is equal, I found it is equal 819.67 ohms. Okay, we're supposed to use the value which we found for RP. You cannot use the value of the resistance from the series circuit. And you're supposed to obtain the value of 87.84 milliwatts. Let me remind you that in series circuit, right, P, we obtain 87.75 milliwatts. Please compare these two values. We can say that they're very close to each other. So it means that if I'm going to calculate the true power for my series circuit and true power for my parallel equivalent, the values of power are supposed to be the same. So we can say that they're kind of the same. So next we're supposed to find the reactive power. So if QP is equal 1/2, and I'm supposed to write VLP raised to the second power over X of L. This is equal 1/2, and voltage across the inductor is the same like voltage across the resistor, and voltage across the voltage source is equal 12 volts, and of course raised to the second power over X of L, which is equal 657.89 ohms. You're supposed to get the answer 109.44 millivolt ampere reactive. Let me remind you that we found the reactive power for the series circuit equal to 109.69 millivolt ampere reactive. Again, you can see that these two values are very close to each other. So we can say that the problem is solved correctly.